Today we're talking about graphing quadratic functions in standard form. And today students will graph translated and parent quadratic equations. And students will identify a vertex as a minimum or maximum and explain what that means. So first, let's talk about what a quadratic function is. And a quadratic function is basically something in the form of where the biggest term is something like this, where it has an x squared. So like, for example, we've all seen this, right? We know that when we see y equals x squared, this term is has a power of 2, and that tells me that it's a quadratic. We also know that when we graph it, here's our x-axis and here's our y-axis. If we were to make a cute little chart over here for values of x and y, let's just pick a few values for x. If I chose 0 and 1 and -1, I know if I input right here, if I input 0 right here, and for the x, I know y equals 0 squared. Well, that's just 0. And if I input this 1 in for x, that would be 1 squared is 1, and so on for -1 squared is also +1. So if I were to graph that, I'd graph 0, 0, 1, 1, and -1, 1. Well, we know that it's not an absolute value function, it's not a v, and as we get closer and closer to these values, we start to see this curve, okay? This curve that looks like a U is how we would describe that quadratic function. So we know anything with an x squared as its biggest term is going to have some form or shape of this U shape, the quadratic shape. Okay, moving on. One other thing that we know about a quadratic function is this point right here. Notice how there's only one point right in the center, and we call that the vertex, okay? And the vertex, in this case, is through the point 0, 0, but not every parabola has a vertex at 0, 0, and we'll talk about that more. We also see something here, and this is called where it's perfectly symmetrical. We call this the axis of symmetry. Now, sometimes, like this one, it's right on the y-axis, but it's not always. It always goes through the vertex, and it will always cut the quadratic equation in half so that it's perfectly symmetrical on both sides, and we call that the axis of symmetry. So in this case, we would label this as x equals 0 to describe that axis of symmetry. Okay, so now, what if I said, okay, so what if we changed how this looks? What if I asked you, okay, so let's graph a different kind of quadratic equation, y equals 2x squared, okay? So if we did that, it's obviously going to change this form, and we call this is a form y equals a times x squared, because this x squared is our parent function, but the difference is that we are just putting a coefficient, we're multiplying it by that coefficient of a, okay? In this case, the 2 is our a term, or our a value for that coefficient. So just like you would pretty much with any graphing equation, let's go ahead and make a little table to help us decide where we're going to go with this. We're not just coming up with random points. We want to make sure that these make sense. So this is the fun part. You get to make it easy on yourself. Let's pick some values of 0, 1, -1, and let's pick up another one, 2 and -2. So anytime we pick a value for x, we're going to insert it. We're going to insert that value for x into our function, and it will come out with a value for y. So here we go. We know negative 2 squared is positive 4 times 2 is 8. Let's do this one again over here. I know that negative 1 plugged into x is negative 1 squared is positive 1 times 2 is 2. Let's do 0. 0 squared is 0 times 2 is 0. And you get the idea that anytime we pick a value for x, we have a value for y that comes out of the function. 1 squared is 1 times 2 is 2. Last one, 2. In for the x, we go 2 squared is 4 times 2 is 8. Okay? So now that we have those values for x and y, we're going to graph them. So here we go. So we've got negative 2 comma 8. So 1, 2, 3, 4, 5, 6, 7, 8. Right here. Negative 1 comma 2. 0, 0. 1 comma 2 and 2 comma 8. And this is the shape of our parabola. It looks a little different. Not much, I mean, it still has the U shape, but do you see how it's a little bit skinnier than the parent function of y equals x squared? We call this our parent function. And everything is a kind of variation of that parent quadratic function. Okay, so here we have an example where we're graphing a quadratic function, and we know it's a quadratic function because why? Because right here we have an x to the 2 power. And just like before, there's a coefficient in front of it. Remember, we call that an a term because it's a coefficient in front of the x squared. But now we're adding a constant, which just means a number, a constant behind it. So we'll call this a c term, okay? So this is of the form y equals ax squared plus c. Okay, so what would this look like if we were to graph this? So just like before, anytime you're going to graph something, let's make a table of values. Okay, so we're just going to make our own table. And this is where you get to decide what values you want. Now, there are better choices than others. Make it as easy as you can on yourself. Choose a handful, 3 to 5, especially because you have that curved shape. I'm always going to pretty much choose 0 because it's a really easy number to use. And I'll probably usually use 0, 1, and 2. And to the left side, negative 1 and negative 2. So I'm going to go ahead and do as I did before. I'm going to take my value for x and insert it right here for x. So we know negative 2 squared is a positive 4. And then we're going to multiply that negative 1/2 in front of it. So negative 1/2 times 4 is negative 2. Add the 3. So it's like saying negative 2 plus 3, and we got a positive 1. All right, let's do this next one. Negative 1, you insert it here for x. Negative 1 squared is positive 1 times negative 1/2 is negative 1/2. Add the 3, and we get 2.5. Let's do this one. 0. Again, we plug it in here. For 0 squared is 0 times negative 1/2 is 0. Plus the 3 right here is 3. And then we're going to finish this off. Let's do orange. We've got 1. We're going to plug it in right here. 1 squared is 1 times negative 1/2 is negative 1/2. Add the 3. And we get 2.5 again. Do you see a pattern? And the last one, we're going to insert positive 2 into the x squared, so that becomes 4 times negative 1/2 is negative 2, add the 3, and we get 1. So now we're going to use those values to plot our graph. So we've got negative 2 in the x direction and 1 in the y direction. So we go to the negative 2 and up 1 in the y direction. Plot that point. Negative 1 in the x direction, positive, here's 2, here's 3, so here's 2.5 here. And we're going to go, oops, this is actually on the y-axis, isn't it? And then we've got 0, 3. So here's our 3. 1, 2.5. And 2, 1. So those are our points. Now we're just going to make a round, nice curve out of those points. And do you see something different? Before, the U-shapes that we saw out of the quadratic function were going up. This one happens to be going down. Notice how it has something to do with this negative that we put in place of it. So when there's a negative in front of your A term or your quadratic term, it becomes sad because it's negative, so it goes down. It's not a smile anymore, it's a frown. Now let's go ahead and compare what this looks like compared to the original parent function. Now remember, the parent function was just y equals x squared, right? And when we did that, started at 0 and it came up this way. Okay, so how are these similar and how are they different? Well, they both have that U shape, right? They both have the same axis of symmetry right down the middle. So the abbreviation for that is AOS, axis of symmetry at x equals 0. Okay, but how are they different? Well, the parent function opens upward, and the graph of y equals -1/2 x squared plus 3 opens downward, right? And we talked about that because of that negative in front. So we know that this function opens downward. Sorry, that looks weird. That's downward. And we also see that the vertex of the parent function was at 0, 0, but the vertex here at this graph here is up 3. And that's because that C value, that adding 3 here, actually moved the vertex up. So we know that the C value will move the vertex up or down based on what it is. Okay. Okay, so now let's talk about what this idea of standard form is. So we've looked at quadratic equations. We've looked at this coefficient in front of the x squared. We call that a. We've looked at this constant in the end that we add, and it makes the vertex go up and down. But what is all this stuff? Okay, so let's talk about this. The standard form of a quadratic equation is y equals a x squared plus b plus c. And I sometimes think of standard form like it's pretty standard when you went to preschool that you learned the A, B, C's. And the standard form of a quadratic equation tells us a few things. A tells us if it's positive, it's going to go upwards. If it's negative, it's sad. It's going to go upside down, okay? It also tells us, depending on what number it is, if it's going to be very wide or if it's very skinny, okay? The C value, we already talked about this, but the C value tells us that it's going to go up if it's positive, and it's going to go down if it's negative, and that changes where the vertex is by up or down. The B value does something very interesting. Now, we can't exactly find it on the graph, but it does tell us something very important about the vertex. The B value is really important because it tells us where the vertex is. We know part of the vertex is the x-coordinate of the vertex. Now remember, that's just the x-coordinate. a point has two coordinates, an x-coordinate and a y-coordinate. This just tells us the x-coordinate equals negative times the b value over 2a. So what's kind of fun about this standard form is instead of graphing things out and finding where the vertex is after, we can find it directly based on the equation that they give us. That the vertex is x equals y equals x equals negative b over 2a. And then to find the other point of that vertex, you would just plug in the x. So let me show you how to do that, okay? So here we go. Let's say, for example, we've got y equals 2x squared minus 8x plus 6. So let's just make things easier on our eyes, and we're going to label A, B, C. So remember, we know A, B, C. And I'm just going to write them over here so I have easy access to them. Keep in mind, whatever sign is in front goes on that number. If this is a positive, I know it's a positive 6 and so on. Okay, so remember, we know that because the A value is 2, it's positive, so it's going to be going upwards. We know C is 6, so that's shifting everything upwards on the vertex by 6 units. And let's find the vertex directly. So remember, x equals negative b over 2a. So if I plug those values in, I know b is negative 8. So a negative b would be a negative 8. Because if my b value is negative 8, I'm just putting it inside that parentheses. And then we're going to put it over 2 times the a value right here, which is 2. And we know how to do that math. A negative times a negative is a positive. 2 times 2 is 4. If we can simplify that, that's our 2. So we know that our vertex x equals 2. Well, hold on a second. A point has to have 2 coordinates, right? It's not enough to just have x equals 2. We can't plot that. So in order to find the rest of the vertex, we know y equals 2x squared minus 8x plus 6. Well, we just found what x is at the vertex. So to find the y coordinate at the vertex, we're going to plug in x equals 2 every time I see x. So the y coordinate of the vertex is 2 times 2 squared minus 8 times 2 plus 6. And then we just evaluate. We know PEMDAS, remember? Order of operations. We're going to do our exponents first. That's 4 times 2 is 8 minus 8 times 2 is 16 plus 6. 8 minus 6 is negative 8 plus 6, and we get negative 2. So at the vertex, we found up here that x equals 2 and that y equals negative 2. So we call that a coordinate point. So our vertex is at 2, negative 2. So let's go ahead and graph that really quick. What's really great about finding the vertex first is that here's 2, here's negative 2. We already know that it's going to be symmetrical about that point. We also know, if we know where the vertex is, we know where the axis of symmetry is. This axis of symmetry is x equals 2. A little hint for you, the vertex is that point here. Whatever this value of x is, the axis of symmetry is the same value. So these two values of x are the same, okay? So little hint for you there, saves you some brain power. Okay, so there's our axis of symmetry. And now we just need a couple more points to flesh out what's going on in this standard form of the equation. So let's look at the right and the left of what's going on. So we know that if the x value for the vertex is at 2, the right and the left of that would be like a value like 1 and 3. So let's make a little graph here, and we're going to plug it back into our original equation. 2x squared minus 8x plus 6. So here we go. Let's just plug these values in for x. So 1 squared is 1 times 2 is 2, minus 8 times 1 is 8, plus 6. And we get 0. And then we plug 3 in here. So we go 3 squared is 9 times 2 is 18, minus 8 times 3 is 24, plus the 6. And we also get 0. So that's kind of fun because we know those points are 1, 0, and 3, 0. And we can finish out that parabola. Okay, it took a long time because I'm walking you through it, but what's nice about that is especially when we have something in standard form, we don't always know where the vertex is going to be. So plugging in random values won't always get us that nice U shape that we really want. So find the vertex first, know where you're coming from, and then pick a left to the left of the vertex and the right of the vertex to finish out the shape of your parabola. Okay, so now here's a key concept. Okay, so we've been looking at these parabolas. We've been able to identify the different parts of them. We know there's a vertex and that there's symmetry. Okay, so here's a key concept. For the parabola in standard form, y equals ax squared plus bx plus c, we know that it has a vertex, right? Well, we've been talking a lot about the x value of the vertex, but the vertex has the y-coordinate. So the vertex's y-coordinate is really important because that y-coordinate is the minimum or maximum value of the function. Okay, and here's how to know which is which. Okay, let's do a little graph first, okay? Now we talked about those little pieces A, B, and C, what we know. We know if A is positive, okay, or we could say A is greater than 0, we know that the graph will be happy, right? Because it's positive, so it's going upwards. We also know that if the A value is negative or less than 0, okay, we know that it's going to go upside down. It's going to be unhappy, right? Well, where's the vertex? Okay, we know the vertex is here because there's right in the center of that curve, and here's the vertex. Here's how we can tell if it's a maximum or minimum. When we're looking at this red parabola over here to the left, what is the vertex to you? Does that look like the lowest point or does it look like the highest point? Well, it's pretty obvious. We know this is the lowest point, so we call this the minimum value. So when A is positive, the vertex has a minimum value. And when we're looking over here, we see this vertex. It's the highest point of the parabola. We call that a maximum value. So when A is negative or less than 0, the vertex has a maximum value. So when A is positive or greater than 0, it's a minimum. When A is negative or less than 0, it's a maximum. So why do we care about this? Why is this a big deal? Well, here's why this is a big deal. We use this all the time in real life, in business especially. So here's when we would need to say whether or not something is a maximum or a minimum value. Okay, so I told you we're going to figure out why this is so important to us. And here is why a lot of people think this is important, because of this little thing right here. Lots of people like money, and it's an essential part of our daily lives. People who are in business are not in business so they can figure out how to make the minimal amount of money that they need. They're in business to make the most or maximize the amount of money that they can make, right? So let's figure out how we can actually use a parabola to figure out how we can maximize a business. Okay, so let's just say Bob has a go-kart racing business, and this is my very, very sad attempt at a go-kart. It's really bad. Anyway, he has a go-kart business, okay? And he, right now, has about 300, well, I should say not right now, pre-COVID, has about 380 visitors per week who ride his go-karts. And he charges $35 per race, okay? Now, what do you think would happen if he lowered his price? You might guessed it. Hopefully you guessed it. He's going to get more people. So anytime we lower the price, there's more interest in what we're doing, right? That's called supply and demand. Little preview for your economics course. So he figures, well, there's about, every time he does a special, every time he lowers the cost by minus $1, he gets about 20 visitors more per week that he gains. Okay, so he has more people coming if he lowers his price a little bit. Now, obviously, we don't want to lower his price so much that he has too many people and the lines are too long and it's costing him something, right? So we want to figure out what's that sweet spot. What should he do to really maximize his business and make the most that he can with the most amount of people he can. So here's how we're going to do it. We're going to talk about how does a business run? Well, there's this thing called revenue, which is how much money is brought in at the end of the day, okay? And revenue is, in this case, is the price times the number of attendees, okay, right? So if our price was $35, but we're saying, okay, how much should we subtract from that, right? How much should we decrease? We're going to say let X equal the discount, right? Or how much we're discounting the original price times. Now, we do know that every time we reduce the money by $1, Bob figures out, okay, there's 20 visitors more. So right now, normally we have 380 attendees, right? And as we subtract every $1 here, we add 20 more people. So for every $1 in price, we add 20 attendees, okay? So let's figure this out. So revenue, we'll call this a function of R of X, where the price is 35 minus X. We're trying to figure out how to maximize it, right? And we're going to multiply it by 380 plus 20X. All right, so let's just do that math, okay? We're going to use our faithful friend FOIL to multiply binomials. And here we go. We're going to go 35 times 380, that gives me 13,300. Outer, that gives me a positive 700x. Inner gives me a minus 380x. And the last term is a negative 20x squared. Well, what do we have here? What we're looking at is we're just looking at a quadratic function. So we know this is our biggest power, so we're going to put that first. We put that in descending order. Negative 30, 380, and 700, if we combine them, because these are like terms, actually, we're going to simplify that, and we've got 300, It's still on erase. Silly, silly. So 320x, and there's our 13,300. So here we go. We know our function for all of his revenue is this. So remember, we want to maximize it. So what are we really wanting to find? What piece of information would tell us where the maximum is? Okay, if you said vertex, you're right. So remember, for vertex, we know the vertex x coordinate equals negative b over 2a. Well, we have a quadratic function here, don't we? We have our values of a x squared plus b x plus c. So here, let's write this down. A is negative 20, b is 320, and c is 13,300. Let's see if we can find this vertex in order to maximize it. So here we go. The x value of the vertex is negative b all over 2 times a. So we've got negative 320 divided by negative 40. Well, we know a negative divided by a negative is a positive. We can cancel out these zeros because they both divide by 10. And 32 over 4 is 8. So if x is 8, does that tell me what our maximum revenue is? No. It tells me what our, remember what we said x should be? We said x was the discount, right? Well, we said we decided in order to maximize revenue, we need to discount the price by 8. Well, let's find out that total revenue, right? So if we know R of X, meaning that the discount is now 8, equals negative 20 times 8 squared plus 320 times 8 plus 13,300, which we got all from right here. And now we're going to find that value of our y, okay? This function, is, you can replace it with the value of y in order to find that maximum vertex. So here we go. We plug in the value of 8 in for that we got from the vertex. Now here comes our value for y on the vertex. So here we go. And we're going to use, I'm just going to use my calculator for this, okay? And we've got 14,580. So that's his maximum revenue, which is a really fun way to be able to do it, because that way, you know, poor Bob doesn't have to run a special every day to figure out what this would look like. He can actually use math to know exactly what he should charge right from the get-go. Okay, so since we're in mathematical analysis, we're going to analyze the quadratic functions. We're going to find out, are they maximum or are they going to have a minimum vertex, and what is it? So here's a quadratic function here. So looking at this, remember that when we looked at, okay, what are those a, b, and c values? So remember, we put it in descending order, make sure that we have it in our x squared term is the biggest, so this is our a value, this is our b value, this is our c value. Which of these values tells us if it's a maximum or minimum? If you said A, you're correct. So remember, if A is positive or greater than 0, we know it has a minimum because it looks like this. And if A is negative or less than 0, we know it has a maximum because we know the shape of it looks like this, and this vertex would be at the very top, which would be a maximum value. So we remember those two little pieces of information to help us decide which of these we're dealing with. So let's look at our value right here. What's our value for A? It's a positive 3. So because we know it's a positive 3, we know the shape of the function will look like a happy face, and it will mean that the vertex is down here, it's low. So this is going to be a minimum value. So now that we know it will be a minimum value, we want to find out, okay, what is the minimum value? Remember, the minimum value is the y value of the vertex. In order to find the vertex, we first have to start off with the x. Once we find x, we can find y. So here we go. Let's go ahead and label what we've got here. We've got A, B, and C. Here's A is 3, B is negative 18, and C is 20. So we're going to use this information to find our x value of the vertex first. Here's our negative B over 2A. Now remember, it's a negative B, so we put the negative out front. Put your parentheses around it so you don't forget that the B just goes in the parentheses and you don't worry about the negatives till later, okay? So here we go. We know a negative times a negative is a positive. That leaves me with 18 over 2 times 3 is 6. 18 over 6 is 3. So at the vertex, x equals 3. So what is the vertex? Well, remember we have to plug this back in, x equals 3, into our original equation here. So we've got y equals 3x squared, I almost forgot what it is, minus 18x plus 20. So in order to find out what this y value is, which would be our minimum value, we're going to plug in those values for x. So we plug them in here, here, and that's it. So y equals 3 times 3 squared minus 18 times 3 plus 20. And we've got 3 squared is 9 times 3 is 27. 18 times 3, what is that? 9 times 6, that's 54, plus 20. And then we're going to do that math. That's 47, 54, so that's going to be a negative 7. So we know the minimum value for that vertex is y equals negative 7. And if I wanted to graph it, I know I'd have to say, well, x is 1, 2, 3, and y is 1, 2, 3, 4, 5, 6, 7. It's way down here. And then our graph would look something like this. Okay. All right, that's it for our lesson today. We're going to do this practice in our next class during our session where we're going to get to practice. We're going to collaborate on all of our fun quadratic equations and minimum and maximum value.